Alright, hey, welcome to this video. I am Félicien Legrand, Sales Manager here at Gentek EO. Happy to spend some time with you guys talking about protecting people, systems and facilities by doing safe laser beam diagnostics. Safe laser beam diagnostic, not exactly what you're seeing right now on this slide, those pictures. The goal today is to avoid those situations and to learn from that to make sure systems and operation are safer and more efficient. Okay, first of all, Gentek EO, we are your partners for accuracy. We've been an independent company since the 70s with the headquarters in Quebec City, Quebec, Canada, with offices in the US and in Japan as well. We do design and manufacture laser measurement solutions, power meters, energy meters, beam profiling cameras, and terahertz power and energy measurement solutions. The picture that you see on this slide here, that's the first spec sheet of the first joule meter that was introduced on the market in the 70s. We offer best practices for accurate measurements and guide our users to get the most out of their laser systems by doing proper measurements. Okay, safety, it is not just only about human exposure. Of course it is. We need to protect people from those dangerous beams, but being safe around lasers, it's not only about protecting from direct hazards, protecting the skin and eyes. Being efficient with lasers, it's not only about improving speed, amplification, compression, delivery optics, heat extraction, and so on, and so on. Because light target interaction matters. You want to know where does the energy go, right? It does not take a lot of power to light up a match, for example. A few hundreds of milliwatts and you could start a fire, for example, such as shown in this picture here. So, okay, when you see this, that's a picture of a water-cooled based power meter returned to us that was severely damaged. The idea was to help those users to prevent this kind of situation. Basically, the beam was focused and was not defocused, and the beam was collimated, and that was a very dangerous kind of setup. But I want to be very clear here on this presentation. I will present a few of those examples here, again, for educational purposes and to help people to prevent and avoid these kind of situations. So, yeah, no judgment. Things happen, and we're here to learn, right? Okay, so there are two kinds of threats to humans and equipment. First one is indirect. When you have a bad laser beam diagnostics that's done and that could compromise operation. I'm talking how do you calibrate a laser, for example. Well, we all want our eye surgery lasers to be well calibrated for safe and efficient operations, right? And then there is an indirect threat when the detector is not used within specs, or for example in those two pictures, when the beam is targeting not the right area on the detector itself. So that could start a fire and pose a lot of hazards. Okay, we take a systemic approach in the sense that protecting people, that is the end goal, of course. But then we consider diagnostics and targets as part of the hazard change, and we're taking in consideration all the aspects, the lasers, the sources, the targets, the optical components, and the facility and the systems and so on. Good, safe, accurate laser performance diagnostics will help to improve the processes and confidence in the laser product reliability. In this context, that will help to anticipate failure modes of the laser systems, help to reduce system maintenance costs, reduce paperwork, reporting, and so on, help to protect assets, secure facilities, and potentially increase the budgets because you will have to replace your detectors less often, for example, and take advantage of your laser system and use it more often, less downtime, these kind of things. So we like to think outside of the laser safety box per se. This presentation was initially prepared for a laser safety officer community, but the message was kind of broad and we adapted it to a general audience. So yeah, it's not just about protecting eyes and skin, it's about protecting everything that's around the lasers, basically. Okay, there are three types of measurements, right? Good, bad, and ugly. The good one is representative, is accurate, it's traceable to NIST standards, and so on. Some people do not care that much about accuracy, but they value more the repeatability from one moment to another. Do I get the consistent reading between measurement sessions? Then, so both traceable and absolute and sometimes just repeatable is considered as good. But then you have the bad scenario when the measurement is somehow safe, right? Does not represent a hazard, but it is useless because the calibration of the detector is overdue. There are some invisible damage. The detector could be saturated, overheated, misaligned. Signal to noise ratio could be bad. They could have some offsets resulting from a bad zeroing procedures and so on. Potentially the wavelength of the laser is not properly paired with the capabilities of the detectors and resulting in some offsets and so on. As you can see on those targets, it is not centered, it is spread out, it is not a good measurement. And then the third type, it is the ugly scenario where the measurement is useless and dangerous for, again, people or material or, in the end, both. Okay, so our motto is Partners for Accuracy. Why? Because we like to provide the most accurate measurement for the application of our users. We define measurement accuracy as the combination of two things. First, repeatability, which is a random error, and then the calibration uncertainty, which is a systematic error. As you can see on those targets, when you combine the two, repeatability and calibration uncertainty, you get all your measurements centered around a given average value, and that's on the center of the target here. On the right side of the slide, you see what we call the Personal Wavelength Correction Certificate, which is a document that we provide for every detector. We do measure the absorption of every detector that we offer. This is to decrease the calibration uncertainty and to be sure that we use the proper absorption value. Using a NIST traceable spectral photometer, we measure the absorption of all the detectors and we load those calibration coefficients in the EEPROM, the electronics of those detectors. So when you enter your wavelength in your control interface, it will retrieve the proper calibration and the proper absorption value to derive a more accurate measurement with the uncertainty the lowest as possible. Okay, what is the cost of bad measurement? Let's say if you're underestimating power, resulting in a power level that's actually higher in the field, that will be unsafe because you have too much power that is not expected. Then if you're overestimating your laser power level, and in the end the power level is lower, that will result in a system misused, an inefficient laser system. You will have to process longer this part to cut it well in and so on. Then if you have false beam quality data, could result, I'm talking beam profiling with some hotspots and stuff, that could result in unexpected exposure zones, potential hotspots in the back reflection going back to the system or to potential users, which is dangerous. Then misleading laser acceptance tests. Of course, if you have bad measurement, you will report wrong data, and for an audit, for some compliance and traceability purposes, quality control, this is not good. And the risk to personal and optical components will be increased. Okay, again, on the cost of bad measurements, if the detector that's used is not a good fit for the application, you will have to potentially replace it, or whether or not it is damaged, resulting in downtime which has a cost in your operations, potentially damaged optical components, need to investigate, do additional tests, reporting, and so on. You potentially will have to recalibrate more often, not every year, not every 2 years, potentially every 6 months and so on, if it is not well used and properly used within specs or for the type of laser. And then if you're a laser manufacturer or system provider, on reputation, if you're casting doubts on the laser performance because of wrong measurements, this is a bad scenario. Okay, so if we consider measurement as a safety function, then we acknowledge that measurement errors will drive unsafe decisions downstream, and then you will be able to protect people from stray beam, back reflections, overheating parts, damages, unexpected laser power, and so on. You will be able to protect system if you integrate measurements this way by controlling performances, plan for field service regularly, or maintenance of the system accurately, increase confidence and so on, and then protect facility in the end because you will be better at managing downtime, reporting duties, and manage better those fire alarms. You don't want fire alarms. Okay, this is a chart could be used as a reference if that has any value for your operation and work. This is a chart of pulsed lasers, the state of things as we are right now in 2026. 5 main categories. There are many other variations of that, of course, but this is to give you an example of that. Depending on the pulse energy, the pulse width, the rep rates, we're in a field where most of the time the average power increases. whether it's for scientific application, medical, telecom, ultra-fast, micro-machining or macro-machining, and extreme pulse laser systems for direct energy or fusion drivers and so on. We're in this realm of increasing the average power. For pulse lasers and for CW lasers, power is increasing. So that represents a good challenge for us and for our users to measure that safely. Please use this chart that could be of some inspiration for your work, and let us know if you have any question how to measure specific lasers inside of that properly with the right detectors. So system efficiency is not only about better lasers. If we consider that and think as a system, diagnostics tools will face extreme environments. We're talking kilowatt pyroelectric detectors, megawatt power meters, 10 petawatt beam dumps, as we could see on the picture on the right here that was delivered to a research facility. Whether you're running internal, a peak-off, matching a driving current with a resulting output power, documenting laser medium aging and so on, that's internal in a system, or you're going external for calibration in the field, free space, fiber coupled, run factory controls, field service, set your lab things and so on. Whether you're doing this or that, the diagnostics tool will become vulnerable, and you will want to protect the system from the back reflection coming from this beam dump or power meter. So not just again about eye injury or hazards or skin exposure. It is of course very important, but if you have a laser that's not properly behaving, that will pose a much larger threat to operations. An example here, if you take a new laser that's overperforming on the spec that could look good, right? Oh, it is providing 110 watts, but it is specified for 100 watts, looking better. But if you're running calculation as a laser safety officer, that will result in wrong assumptions and wrong strategy potentially down the line. If you have an old laser, on the other hand, which is underperforming with some degradation of optical components and a lower performance level, you will need to adjust the attenuation process, the attenuation amount, and the process in the end. So, power is increasing, energy level is increasing. Don't get me started on laser pointers that you could find available online, but all laser systems in professional and research facilities, if they are combined with their diagnostics tool, they represent a system that we need to measure and take care of. So, and I want to emphasize on the fact, so our users, they want to process their targets, right? You want to process your material, the tissues, the sensors, samples, the hologram if you're doing inertial confinement fusion. This is the goal of the laser, is to process the part, right? To do something to it. But as far as power meters, joule meters being providers, ideally you don't want to compromise them. You want to get the best accuracy, and ideally they could remain the same forever, and you don't want to change them, you don't want to touch them. It could provide something reliable. But whether that's a thermopile, pyroelectric, photodiode sensor, CMOS sensor, indeed they are designed to absorb photons and provide a calibrated electrical signal that we will use to make a measurement. But even if often they are assumed to be safe by default, use this power meter and measure the beam. Most of the time, full disclaimer, they are not. You need to pay attention to how they're used and how they're selected. We provide tools to make that easy. As for selecting the right detectors, that's a product finder we offer online. Whether that's for CW pulse lasers, you enter the wavelength, pulse width, energy levels, and repetition rate, and the beam diameter that's expected in the application and the beam profile. And you will get a pre-selection of detectors amongst our hundreds of standard products from picowatt capability up to hundreds of kilowatts depending on the technology. Just to give you a chart here of examples, same for pulse-to-pulse energy measurements, if it's a pulse laser, to hundreds of kilohertz, femtojoules up to kilojoule level. The product finder is pretty efficient, finding the right spot, finding the right technology for those needs. And then, let's say you have a detector in your lab or in your facility that's been there for a while, calibrated or not, and you want to be sure it could be used for your laser line. There's a tool. You go to the product's webpage, you use this test your laser compatibility tool, enter your laser parameters, and you will get a go, no-go, and a calculation of the exact DAMA thresholds for those conditions. So, which could be very valuable to decide if you could use it or not. So problems are starting when you have the same laser, but you get different readings, whether this is from one detector to another, or with the same detector used at different moments. Detector responds, but you will have those bad measurement scenario with the targets with some spread out measurements and not good repeatability. So even your reading could drift over time, depending on the type of misbehavior that you see. That could be some reading drifting, over time, or a consistent offset between different detectors. An offset that could vary between measurements. Is that a zeroing issue? People could run various different types of zeroing features, but there are some tools on software that are usually very easy to use. You could see some nonlinearity with power or energy, or bad repeatability, depending on the beam position or incidence angle, and some wear or damages internally that's potentially not always visible. So in those cases, first question is that, is the detector used within specs, right? And then, do I need to consider recalibration with a potential repair? Question is that, is it coming from the laser again, or the detector? And if we're considering recalibration and repair, the key idea here is to build the detector's history. When the detector is received, recalibrated, we do an as left versus as received sensitivity measurement, and we gather all this data again to see how the sensitivity has been drifting over time, to potentially advise on how to use the detector differently, or how potentially change the detector for a given application. And all this data is recorded and made available to the users to build the detector's history. Key is to design good diagnostics, right? Proper detector head selection first, then implement good alignment practices. Consider beam expansion, defocusing, and or attenuation. And there are three types of damage thresholds. First one is the total thermal load coming from the laser power itself, but the ambient heat as well surrounding the system. So total amount of heat, then the power density, which is the power divided by the surface area touching the detector, that could usually lead to internal damages from overheating. Then energy density damage threshold, which is the energy in joule divided by the surface area, that potentially leading to surface damages. And you could have a combination of the three things, resulting in some bad scenarios and bad damages on the detectors. The key here most of the time is to expand the laser beam. Damage thresholds are well listed in given conditions, but depending on the application, they could vary quite a lot. An example of a good optical peak-off, pretty standard setup here with two wedges, semi-transparent mirrors, where you could place various types of detectors, beam dumps, pulse-to-pulse energy measurement, beam profilers, and so on. Goal is to have an inline way to measure the power energy at a decreased level. And there are some compact systems. Yes, sometimes we do get in a lab and run some measurements with those. That's an example of dual wedge beam splitter system with typically 92% of the incoming beam power that's transmitted through the first wedge at 1070 nanometers, then reflected off the surface of the first wedge goes to the second one, in transmission goes to a power meter, in reflection off the surface of the second one goes to a beam profiler. So you have a tool for inline power or energy and beam profile measurement. So that's great to attenuate down to safe level. Those systems in this package here goes up to 500 watts. If you add water lines, it could go higher to kilowatt range. Example here on the left side, that's a pulse-to-pulse energy measurement at the 1 millijoule level with a attenuator in front of the pyroelectric detectors to increase the damage thresholds up to typically 16 joule per square centimeter. So that was to illustrate how you could just increase the energy level safely without the need to expand the beam necessarily in this case. And on the right side, you see a single pulse power meter calibrated for 5-second shots up to 10 kilowatts. That's the one, and you see the red spot. Grabbing all the beam energy and with a defocusing lens in front of it to make it safe, and then a beam profiler with a camera lens looking at the back reflection off the surface of the power meter to run safe inline both power and beam profile measurement in this case. So good diagnostics. Okay, how detectors get damaged? That's the fun part. We listed 7 types of, let's say, categories of damages. As you can see here, power, energy density, thermal load, peak power, which is defined as the pulse energy divided by the pulse width, rep rate, spectral response, water issues, and errare humanum est, which is the Latin for humans make mistakes, right? We're here to learn from our mistakes and get better. First one, okay, power, energy density. Please have a look at those pictures here. This is typically when detectors' surfaces get discolored, marked, get some spotting, ablation of coatings, and so on. Typically when we use, let's say 19 millimeter power meter, and we say expand your beam diameter to 10 millimeter. If you're not so familiar with that, it is common to program your laser engraver to draw a circle of 10 millimeter diameters. And we see that pretty often. It is not a matter of drawing a given shape, it is a matter of expanding the beam spot size and using a defocusing length or the natural divergence of the beam, placing the detector further away from the source. The wobbling patterns that you could see on picture 3, usually they do not help because the energy density level is just the same. It is not going fast enough, the dwell time is not that small to help potentially decrease the received energy locally. This is all resulting in external or internal melting of coating, glues, thermocouples, piezoelectric crystals, some pretty bad damages here. If you look at pictures 5 and 6, when you align your laser before firing, you will need to be placed and have the beam centered and ideally covering, let's say, 90% or 80% of the surface area. But the goal is not to place the detector when the beam is on. That will hit the housing and compromise the integrity of the detector, and resulting, most of all, in specular reflection. It could be very dangerous for the users. When you have those defects, sometimes it is not a huge deal depending on the type of defects if you're looking for repeatability, because the local minor absorbing defects will add a given offset or uncertainty which could be repeatable. Again, it depends. But if your goal is to get accurate measurements, that won't work. Accurate meaning absolute in this scenario. Okay, so here this is an example of a setup we did for a 5 kilowatt fiber laser system with a beam expander in front. And so I said 90% to be covered by the laser beam. The recommendation is actually 50%. We do recommend to cover 50% of the absorber surface area. So for this that's a 100 millimeter water-based calorimeter here. So 50% of that results in a like 75 to 80 millimeter beam that's covering the surface area using a defocusing length. So that's the best way to proceed if you have the space available. Okay, the second one, thermal load. Yeah, that's the realm of accumulated heat and some cooling issues. Even if the beam is not that small sometimes, because the damage thresholds in power and energy density decreases with the laser average power and the ambient temperature. The typical failure modes here is looking like some radial cracks due to thermal stress, as you can see on picture 1. Some melted absorber surfaces, for example, resulting in bad specular reflections, if you look at picture 2 and 3, and we're not always able to resurface those detectors. If you take 2 and 3, those are water-based calorimeters where we use either copper or aluminum masses right behind the absorber itself. And as you can see, the mass started to melt, so we cannot replace that easily. We need to change the entire surface and the metallic mass underneath. When using the water-based calorimeter, if it gets too hot around, because it is relying, again, on two things, temperature measurement, water temperature measurement, and water flow rate measurement, if you have a too hot environment, that will result in an overestimation of the laser power with those HP water-based calorimeter. Measurement will appear too high because of a too hot environment. And if it's for using thermocouple-based UP detectors, if it is too hot, you will get to a regime where the thermocouple response gets saturated. So the measurement will be underestimated in this case. It's good to know those kind of defects because I will help to anticipate what you could see in the field if you have those situations. Solution here is of course, to extract the thermal heat load properly, considering three things. Again, laser beam itself, the enclosure in which the detectors are placed, and the environment again around the systems. This is all resulting in a buildup of temperature. If you take the example of this QE195 piezoelectric detector, large area one, up to 350 watts capable, 200 hertz down to a few microjoules up to 700 joules per shot. Yeah, it takes 350 watts continuously. Is that enough for the application? Could we build up a customized heatsink or some water lines? Do we need to adapt to that? Yeah. And we need to take into consideration the duration of the measurement. Watch out the continuous versus 1 minute measurement specification, because we do provide those specifications. If you're running continuously or versus 1 minute, you could have the possibility to run to a higher power level if it's for a shorter duration. And if we take those single shot power detectors calibrated up for 5 seconds up to 10 kilowatts, that's a picture on the bottom, between shots, you could let it rest to get back to safe levels and be able to run your next measurements. Okay, peak power. So this is the realm of ultra-fast pulses. We all know that for the same energy level, a nanosecond pulse versus a femtosecond pulse won't have the same kind of interaction with the matter it is targeting. Typical damages here, as you can see, coating damages, surface pitting. It is often catastrophic in a sense that compromising the components behind the absorber, because we're talking here an axial energy transfer versus typically radial for thermopile. For pyroelectric detectors, as you could see here, the energy is deposited as kind of an axial transfer, so it goes deeper. And for thermopile detectors, it goes radial, so it is spread out. It's pretty much diffused. So as you can see on the right here, this is a good illustration of, for the same energy level again, a nanosecond versus a femtosecond pulse will have a different kind of impact, and the cut will be sharper with a femtosecond laser. So looking at the peak power density damage threshold, which is the energy density damage threshold for a given pulse width, we typically list, and this is pretty much the case for all detectors provider, it is listed for nanosecond pulses, but the rule of thumb, if you take those values, let's say 1064 nanometers here, 7 nanosecond single shot, we'll list that at 16 joule per square centimeter. If you take this number and you go from nanosecond to picosecond pulses, you could take the number of the damage threshold and rule of thumb divided by 10. If you go from pico to femto, next step, you take the number you got and you divide it by 10 again. This is the rule of thumb, but we could confirm that for exact specifications. Then, again, if you have those marking, looking either black or white or a shade of gray and so on the surface, the absorption locally will be different, so that will result in inconsistent offsets for your measurements. Repetition rate, fourth one. This one is a realm of combined effects, typically. Accumulated pulses at the same spot on the detector at a given damage threshold, or typically when you're just at the damage threshold in energy of your detector. If you hit the same spot again and again, you will start to see those kind of defects on the surface of it. It is typically more severe for pulse UV because the damage threshold does depend on wavelength. And sometimes you could be tempted to do those measurements and to target the surface on the detector that is not damaged. And it works on good region of the absorber. Yeah, but you could get some nonlinear effects, some offsets, added uncertainties, and the lack of space after a while, right? That kind of reminds me of the joke of the remaining eye. Look at the laser with the remaining eye. Here, you could try to measure your laser energy with the remaining good spot on your surface area of the detector, but in the end, it is not a proper way. Measurement is not absolute anymore. If you use a defocus beam this time, a larger one, you could average out the errors and try to get back to some good repeatability, but again, that's not sure. And most of all here, the damaged areas could result in some specular reflections, because you see those white spot here damaged. They will do some bad things to the system if you get some too high back reflected levels. Recoding may be possible here, depending on the damages again. We could repair that potentially. About spectral response, fifth one. So this is when the absorber is not necessarily designed for the wavelength of the laser here. If you take those, so I took those three examples, the H, W, and QED. If you're not using the proper wavelength for which those absorbers are specified, that could result in some heating of unintended region of the detector, potentially resulting in some damages in the end, and most of all, errors in measurements. But the main hazard here, potentially, this is about, again, unexpected reflections. If you take the H1, 193 nanometers up to 20 micron, broadband, flat absorption around 90%, 45 kilowatt per square centimeter damage threshold, fine. If you take the W1, which is made for 193 nanometers up to 10 micron with a damage threshold that's typically higher, 100 kilowatts per square centimeter, it is not made for CO2 lasers, 10.6 micron lasers. It just provides no signal. It becomes a mirror. So everything gets back to your system, becomes a counter, becomes a safety counter. And then if you take the last one, the QED attenuator in front of, in this case, the thermopile detector for power measurements, goes from 266 nanometers up to 2.5 micron for calibrated measurements. You could extend a little bit down in UV or potentially IR, but that's the specification. Up to 100 kilowatts per centimeter, 16 joules per square centimeter, great diameter thresholds, but it is designed to provide a 50% back reflection level. Lambertian, diffuse, but that has to be taken into account in your system designs and considerations. Okay, next, water issues. Yeah, water is used for cooling down detectors, making them safer for use and for your system. For UP detectors, those thermopile detectors, using an array of thermocouples and disks, water represents potentially safety concern. If you do not use enough flow rate or the right temperature range, you could get some overheating and some damages of the detectors. That's one thing. For those HP detectors, the water-based calorimeters, again, we're relying on water temperature measurement, water flow rate measurement, and so water is used for both safety and accuracy concerns. Main issue here, as you could guess, is galvanic corrosion, right, from weighted materials in the cooling circuit. Whether that's, as you could see, those materials, nickel plating, stainless steel, brass, and so on. Typically, so we provide those lists for you to evaluate that, and we could customize potentially if you see materials here not compatible with your water lines and chillers and so on. The picture you see with the arrow, that's going from nickel-plated copper. Yep. After a while, in some bad situation that was totally corroded, and we have to pretty much change everything in this case. And yeah, depending on water quality, you could get some life in it, right? Some algae. So some products could be used to mitigate that, but in some cases that could just clog your lines and result in some bad situations. And then, yeah, we all make mistakes, right? On the top right, that's an example of a CMOS-based profiler with an attempt to cleaning some dust off of the surface of the CMOS. That was not necessarily recommended this way. We made the choice here at Gentek EO to provide CMOS-based beam profilers with no mirrors in front of the CMOS sensor to help to avoid fringing effects. So that's great for beam quality and accuracy and measurement, but that has the effects of right behind the ND filter, you have a bare exposed CMOS sensor. Need to know that, and if you're to try to cleaning off some dust and debris, please consult us before, and could provide some good guidance before you ship it back, for example. Dust will mate on any surface, resulting in inaccuracy. The oil on our fingers and so on and dust will cook under the laser energy for sure. And we all need to be careful with transport, detector drops potentially, cable snaps, and not to forget to turn on the water if you're using water lines and chiller, and power up the fan and turn it on. Yep. Okay, if we take an example, I wanted to spend some time on the inertial confinement fusion, which is a booming field, very, very interesting challenges right now, both on the source development, for the target development and everything, but on the diagnostic side as well. If we take the neodymium dope glass pumped by flash lamps at NIF, for example, it is well known, 10 kilojoule beams, 192 beams, frequency conversion, capable of 1 shot per day, using well-established glass calorimeter technology to measure the single shot energy levels. That's good. If you take that success and try to scale up using ytterbium doped YAG pumped by laser diode stacks or krypton fluoride excimer lasers, we're talking tens of sources within a given enclosure. Let's say 3 joule per pulse, 10 hertz, resulting, for this example, 300 watts within a single enclosure. But we're considering hundreds of beams to make that successfully implemented in the future, right? Resulting in 10 megawatt level power level in future plants, which is a huge amount of heat, a huge deal to manage. It's a huge amount of power. So how could we do that? If we consider 10 hertz, it is a sweet spot for pyroelectric detectors. That's great. They're reactive. They provide good pulse-to-pulse measurement capabilities, but they do need active cooling. So that's a great driver for us as well, for research and development, to come up with new, innovative way of cooling down those detectors using some customized heat sinks, water lines, and so on. The idea is try to make that all safe and repeatable and scalable. Key messages for LSO. Wanted to remind you guys, so this presentation was prepared for the LSO community, but the message is broad, and we just communicate it to anyone, basically. If we look at the duties and responsibility of LSOs here, from the ANSI standard. Three items here struck me as for approving standard operating procedures, making sure that laser is safe, operator is safe, and so on. Implement control measures to evaluate the hazards in work areas. It is not just, okay, there is a hazard because the beam could go there or here and so on. It is when we know we want to block and dump a beam, how does that interact? How the laser matter interaction would potentially represent a hazard? And then ensure proper laser safety training to provide that to user. And yeah, we think that best practices and usage of proper parameters could be implemented in those strategies. So key messages for all. I think we established that measurement errors are a safety hazard, right? Detectors are targets. We need to verify their suitability. Damage is often subtle, internal stuff, and sometimes no, sometimes pretty obvious. Safe diagnostics will drive safer laser use, make people safer, resulting in better systems, and in the end, happier facilities, right? Do we need to train users on measurement limits? I think so. Do we need to challenge measurement assumptions and calibrations? Yep. Do we need to include diagnostics in safety reviews, not just how you could get proper enclosures and strategies and signage and curtains and so on, but we need to talk about parameters as well. Encourage dialogue, reinforce the LSO's preventive role, and most of all, how do you guys watching this is approaching those issues, and how do we implement safe, let's not just call it diagnostics, but just safe laser use in the end. In the name of the entire Gentek EO team, your partners for accuracy on the West US Coast, in our offices there in Portland area, in our headquarters in Quebec City, Quebec, Canada, and in our office in Japan, I want to thank you very much for your attention. Let's interact, let's dialogue, and I'm looking forward to talk to you again.